Hey everyone. Okay, I want you to imagine printing an object that isn't finished when it comes off the printer. In fact, it's just getting started. Now, that might sound like something straight out of science fiction, but it's the reality of a truly groundbreaking technology called 4D printing, and that's what we're diving into today.
We've all heard of 3D printing, right? It's amazing. But what if those objects weren't static? What if they could actually assemble themselves, or change their shape, or even heal themselves after they're created? This is the big question that 4D printing answers.
So, let's quickly break down the difference. 3D printing takes a digital file and turns it into a solid thing, layer by layer. It's totally revolutionary, but the final object is, well, it's fixed. 4D printing takes this to a whole new level by creating objects that are dynamic. They're literally programmed to transform after they're printed.
So to put it simply, 4D printing is just adding the fourth dimension, time, to 3D printing. It's this incredibly powerful idea that an object isn't finished when it leaves the printer. Nope, it's just getting started. All right, so here's our game plan for this explainer. First, we'll dig into what this next dimension really means. Then we'll uncover the secret ingredient, the smart materials that make it all happen, and the triggers that set them off. After that, we'll look at some mind-blowing real-world applications before finally looking at what the future holds.
So, first up, printing's next dimension. We're talking about moving way beyond the limits of just static, unchanging things. And that fourth dimension, time, it just unlocks a whole new world of possibilities. I mean, imagine shipping furniture that's flat-packed, and then you just add water and watch it assemble itself. Or picture a water pipe that can sense a crack and automatically repairs it. That's the kind of incredible functionality we're talking about here.
So how is any of this possible? Well, it all comes down to the secret ingredient, smart materials. You can think of them as the brains of the operation, holding all the pre-programmed instructions for how an object is going to change. Now, there are a few key players in this world of smart materials. Hydrogels are a big one. They react to water, either swelling up or shrinking. Then you've got what are called shape memory polymers, or SMPs. These can be programmed to remember an original shape and snap back to it when triggered. And finally, shape memory alloys, or SMAs, which do the same memory trick, but with metals. And this programmability is absolutely key. See, these materials can be designed for what's called a one-way transformation, where they go from shape A to shape B and just stay there. But, and this is so cool, they can also be two-way, meaning they can automatically go back to their original form. This ability to program complex, multi-step changes is what makes 4D printing so unbelievably powerful. But these transformations don't just happen randomly, right? The object needs some kind of cue, a signal to tell it, okay, time to change. And that's what we call the trigger.
And that trigger can be almost anything in the environment. We can use something as simple as heat or light. We can use an electric field or magnetic field. Or we could even use chemical changes, like a shift in pH or humidity, to tell an object it's time to transform. This gives engineers this incredible level of control over when and how these objects change shape. Okay, let's look at a really clear example. Here we have a simple U-shaped object right off the printer. It's sitting there in its temporary program state. And boom, this shows the concept perfectly. Once an electric field is applied, just watch what happens. Over about a minute, the object unfolds itself, returning to its original straight shape. This isn't CGI. This is a real, physical object transforming completely on command. So this technology isn't just some neat trick in a lab. Let's get to the really exciting part, the real-world applications. Because this is where 4D printing truly starts to feel like the future has arrived. In medicine, just think of stents that can expand perfectly in place, making surgery way less invasive. Or drug capsules that only release their medicine when they reach a certain temperature or pH inside your body. That would make treatment so much more effective. For infrastructure, the potential is massive. Pipes that can heal their own cracks could save billions in repairs, and the list just goes on and on. From that self-assembling furniture we talked about, to shoes that adapt to your activity, to giant structures for space that can deploy themselves once they're in orbit. And a huge source of inspiration for these new technologies is, of course, nature. It's the ultimate engineer. On the left, you've got a harbor seal, and on the right, that's a soft robot called the silicone that perfectly mimics the seal's wavy, amphibious movements. It's bio-inspiration at its absolute best. Here's another incredible example. You have the pufferfish on the left, which inflates itself as a defense. The robotic model on the right, created using 4D printing principles, does the exact same thing. it can inflate its artificial skin in response to an outside trigger. Just amazing.
And the underlying principle of this kind of manufacturing has already proven its worth in a huge way. Now, this example is from 3D printing, but it shows the power of being able to rapidly create solutions in a crisis. During the COVID-19 pandemic, printers like these were used to make desperately needed face shields, showing just how fast this core technology can respond to real-world needs. So, where does all this go from here? Let's wrap up by taking a look at both the massive potential of 4D printing and, the hurdles that we still need to clear. This SWOT analysis gives us a fantastic snapshot of where we're at. The strengths are really clear. These materials can be highly biocompatible, and we can program these super complex transformations. But there are weaknesses. Right now, a lot of these smart materials just don't have the same physical strength as traditional ones, and figuring out how to design them is still incredibly complicated. Now, one of the biggest opportunities on the horizon is bringing machine learning into the picture. Designing these materials and trying to predict how they'll behave is a huge challenge. AI can help researchers speed that process up like crazy, designing and simulating new materials way faster than we ever could before.
And it's really important to keep things in perspective. This quote from the research reminds us that while the potential is just enormous, this is still a very, very new field. We are really in the early days of a technological revolution here. Which leads us to our final thought. The possibilities here are truly staggering. When the things we create are no longer static, but can build, adapt, and even repair themselves, the only real limit is our own imagination. So, what will we imagine next?